Hi, welcome to MEEN 221. Today we are going to start a new topic, what to do when bodies are moving. Up to now we looked at static bodies. Now we are going to look at dynamic bodies. What I want to point out is that at the core level there is not a huge lot of difference. We are still going to draw the free body diagram. We are still going to draw the free body diagram the same way. The main difference is going to be that we are going to add another diagram to it, which is called a kinetic diagram. Okay, so that's our main deal. So what I want you to do is please find a pen, paper, ruler and a calculator so that you can do some of the calculations and you can take notes as we do. Okay, so that's our story. So let's start. What's the big picture here? The big picture is the following. Let me write it down. First thing is we draw and kinematic diagram showing accelerations to the FBD. What I mean by that is I'll have FBD equals kinematic diagram which shows me mass times acceleration. Now this turns out to be a little bit tricky to do because we have to use some calculus here. Here mostly to do this we needed mostly algebra and we have to do calculus for the mass times acceleration vector. The problem for us is acceleration vector is not the same as rate of change of speed. So when you think about your when you're driving your car, there are two parts to it. First part is accelerator or brake. That causes acceleration or deceleration. Right? And this is what we typically think of. But there's another part which is steering. Also causes acceleration. So, or rather also contributes to acceleration. So, not only does the accelerator or brake, but your steering also contributes to acceleration. So I want you to remember this. This part, which is called normal acceleration. Normal, I don't mean common. What I mean is perpendicular. But this is what tells you what happens when you turn the car left or right. This one is whether you go speed up or slow down. So both of them are important. Okay. So our basic idea is going to be force equals to mass times acceleration. So this force side is given by FBD. The mass times acceleration side is given by a kinetic diagram or kinematic diagram. And then we are going to write down the equations. And in this case, we have to do some solution. Okay, so you got the big picture. First thing is acceleration has two components, both rate of change of speed as well as change in direction. So this tells you change in direction. So, change in speed, change in direction, both contribute to acceleration vector. Okay, so let's talk about it a little bit more. The main thing is the following. If you want to solve dynamics diagrams or dynamics problems, you have to decide on the coordinate system first. And the coordinate system is decided by what we know about motion. So, if the path is fully known, so what do I mean if the path is fully known? For example, if it's a baggage handling or if it's a materials handling system, we know the path, we know where this thing is going to go, exactly the path it's going to take, right? Those kinds of extremely controlled situations, we are going to use what are called path coordinates. So your first diagnosis is the path fully known? If the answer is yes, you do path coordinates. Path coordinates are also called tangent normal system. Intuitively, this is the most convenient. So for example, if you're driving along the highway to go from, let's say, from College Station to Houston, you know the path because you know the route of the highway. It is most convenient to use a direction. So here is your highway. It's most convenient to use a direction which is along the path and perpendicular to the path, right? Rather than X and Y, right? That's how. So if you call somebody on the cell phone, you're not going to say I am 30 degrees east and 45 degrees north of where you are. You're going to say, okay, I am 30 miles along highway 6 or something like that, right? So path coordinates are very convenient if your path is fully known. If the answer is, so this is yes and this is no, we don't know the path. The next question is it approximately circular? I don't know the path, but I think it's approximately circular. If the answer is yes, then you use what are called polar coordinates. Then the next question comes about, so this is no. Then the next question is we just use mostly Cartesian. If you don't know anything about the path, it's not circular, we don't really know where it's going, then it's probably best to use Cartesian because that's the easiest one if you don't know anything. But if you know something, this is the best. This is useful for engineering. This is our fallback. Got the idea, right? So that's how, so this is your high level strategic decision that you have to make. Am I going path coordinate? Am I going polar coordinate? Am I going Cartesian coordinate? Okay. So now that we have made a decision, we are going to address these two things. Cartesian coordinates are no big deal, so I'm not going to waste too much time on it, but I'm really going to talk to you about path and polar coordinates. Okay. So path coordinates because that's the physical intuition. Polar coordinates because it's extremely useful and there are some technical issues that we have to deal with. Very good. So let's see what this thing looks like. Path coordinates. Here is the path of something. Let's say you're driving, you're in a race car or something like that. The path coordinate system basically involves fixing, this is my start, and what we are going to do is we are going to use distance along the path as my coordinate. So this is S equal to distance along the path. The direction along the path, this vector is called ET. This is tangent unit vector, tangent to path. And the other vector we are going to use is this one, which is called EN, which is unit vector on concave side. Right? So this is ET and that's EN. That's what we're going to use. Now, I'm not going to do a lot of proofs or anything like that because I think you need to get physical intuition. So first thing is speed. Symbol is V and it is equal to d dt of S, rate of change of distance. That's easy. Velocity. Speed times tangent vector. That is V et. Okay, this is velocity vector. So you can see this is magnitude and this is direction. Okay, then the next thing that we are going to do is acceleration. So I'm going to write acceleration vector is d dt of velocity vector and that turns out to have two parts. If you do dt2, then you do product rule and you will get acceleration vector equals d speed dt et plus speed times det dt. This is change in direction, this is rate of change of speed. Can you see? Acceleration has two parts. Turns out if I want to calculate det dt, you notice at time t et is like that, at time t plus delta t et is like that. So the difference between these two things, if I plot this vector here, the difference is like that. That's what I'm plotting here. So let me write it down. Det dt turns out to be speed over radius of turn times E normal. Okay, that's what it looks like. So we are going to put all these things together. I don't want you to worry about the derivation as long as you realize why it is there. Et is changing direction, so it comes from differentiating this and it has two terms, and et is change in direction. If I take this vector, et is like that, et plus delta t is like that. This vector is in the en direction times some constant, and the constant is called the curvature. If it is very sharply curved like that, you can see there is a huge change in the direction. If it is not very sharply curved, it is not such a huge change. Okay. So to get you an idea of what these things are, let's look at an example. So here is Michael Schumacher in the Formula F1 in Monte Carlo, and you will see it from his point of view. So there, takes off. There, that's what it looks like. Can you see how, now it's really going fast, really fast. Now it's kind of slow. Now it's fast. Now it's really slow. That's because he had to make a turn. Can you see that? So both his turning as well as whether he's going faster or slower, both of them contribute to the acceleration. So this is an example of tangent normal coordinates actually from the point of view of the driver. So you can see sometimes he's going faster or slower, but all the time he's doing adjustments to the steering wheel, right? That also counts as acceleration. Okay? As far as Newton goes, and for that you need forces. So that's how it goes. Okay, so basic idea is, let us summarize. Velocity vector V E T. So the idea is, first find path. Then the velocity vector is V E T, which is speed times tangent to path. Acceleration vector is d velocity vector dt, which turns out to be d dt of speed times et plus speed squared divided by the radius of turn in the en direction. This is concave direction. This is along path. That's what it looks like. So for example, if I am taking a turn like that, the radius of the turn is r, et is this way. So tangent component is rate of change of speed. The normal component is speed squared divided by radius of turn. Right? So now we are ready because we can write down Newton's laws in a very nice way. Oops. So now we have Newton's laws. Force in the tangent, which is force along the path, equals d dt, so mass times d dt of speed. That's easy, no? This is usually called motive force, because this is what is causing the thing to either speed up or slow down. Force normal to path equal to mass times speed squared divided by radius of turn. This is usually called constraint or centripetal component. So usually in the physics class they are fairly sloppy. They'll just call it centripetal force. It's not. What it is that it's called the centripetal component. We are never going to we are just going to say Fn and Ft. We don't really care about whether something is called centripetal or whatever the heck. We don't really care. What we care about is these two things: rate of change of speed and the force perpendicular to path. Now let's look at an example to see if we can figure out how these things work.